Hello everyone, my name is Craig and I'll be your host for today's SDK webinar on multi-domain GNSS challenges. Today's webinar will be delivered by Ted Driver, a senior advisory software developer at AGI, and Tal Bass, a systems engineer at AGI.
Thanks, Craig. I'm Tal Bass, a systems engineer here at AGI. I work in the support department, which means that if you call or email our support line, there is a good chance that I may be the one helping you with your question. I will be assisting with today's webinar, answering questions you may have. Going over the agenda for today, we will cover some background GNSS information and some of the main challenges in the field. More importantly, we'll then show you our approach to solving some of these issues and leave time for questions and answers. So without further ado, I'd like to introduce today's speaker. Our speaker today is Ted Driver. Ted has worked in the navigation field for over 18 years and is an expert in navigational accuracy. Prior to AGI, he was the lead analyst at Air Force GPS Operations Center and has also helped create GPS simulators used to train operators of the GPS constellation. Ted is joining us today from Colorado Springs, Colorado. Ted, take it away.
Thanks, Tal, and thanks everyone for joining our webinar today. You know, whether you're in the design phase or you're in operations of the system you're working on and you're using GNSS for your system's positioning, you're going to run into some issues. And what I'd like to do today is take a look at some of those issues and see how you can mitigate those and then keep your system design from having additional positioning problems and keeping your operations running predictably. So with that, I'll start and talk about the fact that location has been taken for granted for quite a while now. Everybody has devices that have GPS chips in them. With the advent of GPS, Galileo, and GLONASS, multiple GNSS systems, they work so well that everybody just assumes you've got location anytime you need it. Well, we engineers are the ones that keep it that way because we understand the intricacies of that system and how they work. To keep from understanding any problems that are in there, we have to understand the issues that go along with these systems. And so what I want to do is take a look at a couple of these issues this afternoon. I want to start at a high level. I want to talk about two main effects that might affect your positioning accuracy. The first one is signal availability. If there's really no signal from any satellite, you can't calculate a position from it. So that's the main hindrance there. The other one is DOP. It's a geometric artifact from the navigation mathematics. It's something you can't avoid, but it's something that's predictable, and we'll take a look at that next. So DOP, the first issue, is strictly a function of the satellite positions in space and the number of satellites you have in view. In the literature, you can create a matrix G, is what it's typically called, of this different satellite positions for all the satellites you have in space. If you were to take the pseudo inverse of that G matrix, you get a matrix called K, which is the DOP matrix. That K matrix effectively multiplies the pseudo ranges to each of your satellites, which you determine your position from, and it scales or provides a multiplicative factor into the errors you're going to get from GPS. So again, DOP is predictable. It's only a function of the satellite positions. You can lower your DOP by using more satellites in that G matrix. So with the advent of other GNSS constellations like Galileo or GLONASS, you're effectively lowering your DOP as well, which is a good thing. So that's a DOP. Let's talk now a little bit about signal availability. And from this perspective, I want to talk about what might be blocking your signal. There are several different things that could do it. I'm going to talk about just a few here today. But what I'd like to do is start from the top, from the satellite, all the way down to your receiver and inside your receiver's processing. So maybe the satellite's not broadcasting. That might be one of the first things you want to check. Moving down from the satellite to your receiver, terrain might be blocking your signal. If there's no terrain, maybe you're being jammed. If you're not being jammed, maybe you've got antenna gain pattern issues. Perhaps your receiver's dropping signals for some reason. If it's a dynamic platform, you might get drop signals. I want to talk a little bit about receiver noise and understanding how non-constant receiver noise might need to be modeled. And then finally, the receiver processing itself and time to first fix issues. So just to reiterate that if you don't have signals, if your receiver is expecting, say, 20 signals and your terrain might be blocking some, or you might be jammed, or you might be dropping signals, you're losing the number of signals you have, and so that's going to drive DOP up as well. So that also hinders your performance. Okay, so the first one, satellite maintenance. Perhaps the satellite is just not broadcasting. Just like if your computer's not working, the first thing you want to check is whether or not it's plugged in. Maybe the satellite's not broadcasting. All GNSS satellites need maintenance on board, or atomic clocks. They need to be adjusted occasionally. The satellites drift in their orbital planes. The maneuvers have to happen every so often to keep them in the right spot. So they're typically predictable. U.S. Air Force for GPS will send out outage information prior to the event when they know it, so you can predict when these are going to happen. If you're trying to determine your position and expecting a satellite to be there and it actually goes out for maintenance, you're going to be predicting a better position error than you're actually going to get. So the satellite outage information is pretty important. One other thing to keep in mind is once a satellite's been off the air, make sure your almanacs are up to date on your receiver, because if there were orbit maneuvers, those satellites have moved, and if you got an old almanac, that'll tend to exacerbate the time to first fix issues that we're going to talk about in a few minutes here too. All right, moving down from the satellite's broadcasting. Now you might have some terrain issues. Whether it's natural or man-made, terrain will block your GPS signal. There's a picture here from our cesium globe that shows different levels of terrain on the top. Also, if you're on a city, signal reflections from the reflective surfaces will affect the carrier to noise values in your GPS receiver. Not only will the buildings block your signal, just as man-made terrain would, or natural terrain would, but the reflections will affect your carrier to noise. So that's another issue we'll have to deal with. So moving on from terrain, let's talk a little bit about signal jamming. If you could whisper at 1.57 gigahertz, you would completely blow out your GPS signal on your receiver. The signals are well below the noise floor. They are very susceptible to jamming. If you were to find a jammer, in fact, these are some pictures I found just doing image search online. If you were to find a jammer that plugs into your power outlet in your car there, that might typically be a 1-watt jammer or so. A 1-watt jammer will take out GPS in a radius of about 30 miles. These jammers are illegal to sell, they're illegal to buy, and they're illegal to use, so I wouldn't recommend it. In fact, there was a gentleman in Newark, New Jersey about 5 years ago that worked for an engineering firm and drove a company truck around that the employer had put a GPS tracking system on. The employee decided he didn't want the employer knowing where he was at some time, so he bought one of these, put it in, and blocked GPS signals from being tracked on the truck. Well, he happened to drive by an airport near Newark twice a day, and that jammer would take down the ground-based augmentation system at that airport twice a day, stopping all air traffic in and out of that airport. So once they figured out what was going on there, they brought somebody in to direction find where the jamming signal was coming from, and they finally found the guy. And they charged him, and I think he ended up paying like a $35,000 fine or something. So GPS jamming is illegal in the country. It's not something you want to do, but because the signals are so low power, it is very susceptible to that. So what can you do about this? A couple things there. Use more GNSS satellites, or use different frequencies. Maybe use Galileo or GLONASS. Those are not great mitigations, because typically jammers are broadband spread spectrum jammers, and they will jam across the frequency bands for these type of systems. So that's not a great solution. One solution that does tend to work pretty well are dynamic phased array antennas that you can put on your receiver, so that you're getting more power to your signal from the signal sources you want, and less power from those you don't. So that's a pretty good mitigation for signal jamming. Okay, so speaking of antennas, let's talk about antenna gain patterns. Typically on the airplane there, for example, omnidirectional gain patterns are what's used. You can see 4 different signals coming in, and the signal gain applied is where the signal intersects that red circle there. And that's all well and good. For typical civilian aircraft, this is what you would see, and this is what you would get because they don't do any kind of banking maneuvers or anything. But if you were in a military jet, or if you were on any other kind of vehicle that maybe rotates or banks, that antenna is fixed to the body. What's going to happen to those signals and what's going to happen to the gain? So that's a problem you have to take into account, and what your antenna gain might do to the signals. Okay, drop signals. So your signal has made it past your antenna gain, and it's finally into the receiver processing. But if you're on a dynamic vehicle and you're experiencing some Gs or some other kind of maneuvers that are going to cause your receiver to lose lock, you're going to get signal dropouts. Each receiver has got several different channels on it. Each of those channels can track frequencies as well as codes. In fact, it needs to get your position. So you can drop not only codes, but you can drop entire frequencies on each of those channels. So there's a multi-level process there that you have to be aware of. This is problematic for 2 frequency users as well. You may think that, well, I've got 2 frequencies. If I lose one of them, I still got the other frequency on that channel, so I'm still going to get my position. But you haven't considered ionospheric errors in that case. If you were a 2 frequency user, you were using those 2 frequencies to cancel out ionospheric errors. And so now if you're down to 1, you're incurring additional ionospheric errors that you hadn't planned for. So understanding the signal reacquisition modeling will help you keep your system accuracy back to where you need it to be. Okay, from drop signals, we'll move down into receiver noise. Typically, receivers expect noise to be a constant. It's typically a thermal-based noise, and it's constant across all channels, but that's not typically what you would see in the field. Receivers can see non-constant noise, and if you know what that is, you might be able to model that and then get more accurate results in the field. If you don't know what that is, you might be able to go into the field and measure at a surveyed location that you know the location of, and find out how your noise varies as a function of time or as a function of channel. That would let you understand what your non-constant noise models look like. All right, finally, we're on to receiver processing. So essentially, because the GNSS signals are below the noise floor, receivers are integrating noise. And what they have to do is they have to look on 2 different axes here. And in the 2-dimensional graph, the first axis is the code delay, which represents the range to the satellite. So it's trying to determine the range to the satellite. And then the other axis is the Doppler offset. And this is the signal frequency that it's looking for. So the Doppler offset represents the signal Doppler. If the satellite's rising, you're going to have a Doppler offset that's positive. If it's setting, it's going to be negative. So what it's trying to do then is integrate over this range of Dopplers and this range of code chips. And how does it know what Doppler it should look for to begin with? It does that by understanding or looking at the almanac that it's got inside the receiver already. And the almanac will tell you what your rough satellite position is. So it can do a quick calculation to understand what elevation the satellite should be at, and understand what the Doppler from that satellite should be. And so that's how it sets what the Doppler offset bandwidth is there. If your almanac is old, or if you don't have an almanac, it'll start looking for a correlation in that. You can see the peak in the graph there. It'll start looking for that correlation peak as it integrates that noise, but it won't find it. So it will have to expand that Doppler offset bandwidth there and try and integrate again. So as it goes through this process of looking for satellites and correlation peaks over the Doppler offset and the code delay, it can take longer and longer if you don't have an almanac, or if you have an almanac that's really old. The satellites aren't exactly where the almanac said they should be, so it has to keep looking. So this is called the time to first fix problem. Assisted GPS or AGPS on devices that have cellular chips as well as GPS chips or GNSS chips. AGPS can help because it can get a new almanac from cellular networks. They download them and just store them on the cell networks and then send them over to your devices as soon as it boots up and has cellular connectivity. So your receiver will know exactly where the satellites are and reduce your time to first fix. Let's see, I think that's the majority of the issues. So I think right now what we'll do is we'll go to another poll.
Okay, this poll is, what areas of mission system design are you interested in? You can select all that apply: communication modeling, open mission systems, sensor performance, or vehicle design and performance. So again, you can multi-select, and those are communication modeling, open mission systems, sensor performance, and vehicle design and performance. What areas are you interested in? All right, thank you, and we'll send this back on over to Ted. Very good, Ted.
All right, thanks, Craig. Okay, so now we've understood several different problems. Not all the problems you can encounter, of course, but some of them. So now I want to go into how you might mitigate some of these issues and understand what you can do to prevent them, or at least understand them. I'm going to talk about two tools, SDK and SDK components, when I talk about each of these different issues. So let's go back and look at DOP. We talked about the fact that DOP is a result of the satellite positions in space and their orientation. What I didn't talk about was, what good DOPs and bad DOPs are, if you're not familiar. A bad DOP would result from all the satellites being in a straight line across the sky, for example. Good DOPs would be pretty much the opposite of that, having satellites equidistant around your horizon and then satellites directly overhead as well. That'll give you both a good HDOP and a good VDOP, or horizontal DOP and vertical DOP. So on the chart here, on the left, you can see that SDK can produce charts or DOPs for single objects, and this is what a single object DOP looks like over time. The reason it varies, of course, is because the satellites are moving. This is for an object that's not moving on the ground, but the satellites themselves are moving, and so they cause this variance in this DOP value. Remember, it's a multiplier for your position. It's essentially your position error. So higher DOPs represent a higher position error and less accuracy for your position. The picture on the right is a global coverage map for the Galileo constellation using 18 satellites, which is what they'll have when they have their initial operating capability in the near future here. The shape of the colors, the way the colors line up on the map with the two red bands and then the blue bands, those are defined by the DOP from an 18 satellite constellation. The colors of the bands, the reds and the blues, are the actual navigation accuracy for Galileo, assuming you have about a 3-meter uncertainty in the signal itself. So this is the type of navigation accuracy you can expect from Galileo when it's finally online during its initial operating capability. So that's how you can understand DOP. Let's move now on to the satellite outages. We talked about those. I mentioned that the Air Force produces files and information, it's actually called NANUs, that send out outage information for satellites when they know they're going to be out for maintenance. They also produce a file called a satellite outage file, or a soft file, that both the SDK navigation files plugin and SDK components understand. It's a machine-readable XML formatted file. You see a picture or a snippet of one on the upper right there. You can get it from our FTP site, or you can get it from the US Coast Guard site. But using that machine-readable file, you can turn that into usable information on satellite outages and plug those directly into your system. I would highly encourage you to incorporate using this file, especially when you move into operations, because it'll reduce your positioning error based on satellite outages that you may not know about. You don't want to be predicting what your navigation error is when you go out in the field without knowing what the satellite outages are. From satellite outages, we'll move into terrain. Terrain has been a staple here at AGI for a couple of decades at least. In the picture in the upper right, you can see PRN8 following its path down below the mountain there. The receiver, I don't know if I mentioned this either earlier, but receivers typically have a 5-degree mask angle that's a constant 5-degree mask angle above the horizon and all 360 degrees azimuth around you. Below this 5 degrees, your receiver is not going to look for any satellite signals, because as those signals travel through the atmosphere, they get additional errors that the models in the receiver can't correct for. So the receiver, it's expecting this PRN8 in this picture here to drop all the way down to 5 degrees, and then it will throw it out of its solution and start looking for more satellites. But it's going to lose it before it hits 5 degrees because of the terrain here. Your receiver can't know about your local terrain, and so you have to model terrain to understand what your actual navigation accuracy is going to be. We've got both local and server-based terrain products that'll help you achieve this. The picture in the upper right is terrain from a cesium system. The other terrain topic I talked about was the carrier to noise effects you're going to get when you have GNSS signals inside of a city. Just like the terrain where you'll lose your signal, like I talked about, the carrier to noise effects can be calculated using a tool called urban propagation. Those will let you see how your carrier to noise is going to be affected depending on where you are inside that urban canyon. And this picture on the bottom kind of shows that the reflections for the signals past the buildings have a higher C to N0 variance than they would where you're kind of in an open area there. All right, moving on from terrain, we'll go into signal jamming. I talked for a while about how easy it is to jam GNSS signals, and I just wanted to mention that our tools support multispectral jammer modeling. You can take jammers and you can place them on the ground statically, or you can place them on any dynamic platform and have them move with that platform. Both SDK and SDK components support that. The picture in the upper right shows a phased array antenna where you're getting a higher signal attenuation, or I'm sorry, a higher signal gain value in the direction of the satellites that you want to get, and then lower gain values, of course, where you don't want them. I do want to mention that SDK components supports several different GPS signal characteristics, all 3 frequencies on L1, L2, and L5, and all of the codes on those different frequencies from CA, PY, M code, C code, and IQ code. Okay, so from signal jamming, we'll go back to the antenna gain modeling problem that I talked about. Again, you got the antenna gain on the aircraft that's constant, an omni pattern. But as that aircraft rotates, again, you can see how you're going to lose signal gain. One thing you might want to do is add an antenna on the bottom of the aircraft with a similar antenna gain pattern. And now you can see that you're going to get gain while you're upside down as well from those signals. So that might help solve your problem. But where on the aircraft should you put that? Using SDK, you can perform trade studies and place antennas all over the aircraft and find out where the optimal position is for your GPS or GNSS antennas to find out the best signal gain for the system performance that you need to get. Okay, signal drops. Kind of a busy chart. I'm definitely not going to go into everything on the right side of this chart, but I just want to use it as a diagram to show you how SDK components models multi-channel, dual frequency handovers, and all the other options that go along with it. So we support single frequency and dual frequency, all the different options you see there for GPS. In the diagram, the boxes at the top, the blue, represent the different GPS satellites, and then those go into each channel on a receiver. The giant box at the bottom has a single receiver, and the individual red boxes are the channels in those receivers. So each channel, again, has to track not only different frequencies, but different codes on that frequency. What we model in SDK components is the ability to model the handover between CA code to PY code, for example, or from one code to another code based on these different options on the left. So this is just kind of a high level that shows you the depth of the modeling we have in SDK components for advanced navigation communications when you're using GPS. And then using the same diagram, I can talk about receiver noise modeling. As I mentioned before, receiver noise can be non-constant, and what we'll let you do in SDK components is model that on a per channel basis, using all the different attributes, signal power from L1, for example, or from L2, that kind of thing. You'll have access to all the different attributes, including anything else you could use from within SDK components, like jammer sources as noise or something like that. So understanding what the noise is in your system will provide a higher fidelity solution for your system, and it's something you should consider incorporating. All right, receiver processing. So we talked about this two-dimensional graph and how it integrates noise, and it looks for a correlation peak based on different Doppler offsets. If you have an older almanac, you're not going to get the Doppler that you're predicting because that satellite's not in the position it should be. So what you can do in SDK is bring in your different GPS or GNSS satellites, look at the Doppler offset that you would expect from an almanac from today, for example, versus an almanac from, say, 2 weeks ago, and see what the Doppler offset differences are there. So you can plot Doppler shift differences in the tools to understand what width you're going to have to integrate over. And this is how you can model what your time to first fix issues, or some of them anyway, are. I think that wraps up all the issues that I talked about. If I didn't talk about issues that you have or you're interested in, please give us a call, or if you'd like to know more about these different issues, we'd be happy to help you solve your problems.
Ted, I think we do have 2 questions here that I see. So while I want to remind everyone that you can ask questions using the GoToWebinar window, so send those in. I do have some questions here that I can answer, and that is this being recorded and will this be posted? And that is yes, it is recorded, and we will send a follow-up link in an email following up this webinar that has the video posted and everything like that. So, so stay tuned for that. Look for your email. It'll be in there. Ted, I think you can answer this one. How long can you use a GPS almanac?
So that is a good question. Almanacs can typically be used or should be updated as soon as a new one comes out. However, if you don't have the ability to update your almanac, you can use one for up to about 2 weeks or so. After about 2 weeks, I would expect some of the satellites might have undergone some maintenance and then moved, so that almanac is really just going to start hurting you rather than helping you. So I wouldn't use it longer than about 2 weeks.
We have another question for you, Ted. I think it might be you, but it could be Tal. Can SDK model all of the GNSS constellations?
I'll go ahead and take that. We can. So SDK can model the GNSS constellations, GLONASS, Galileo. You can calculate DOP with those. You can calculate navigation accuracy with those. You can bring in all the different constellations and find out how your system performance is going to be affected by using them or not using them, seeing how many you can bring into a receiver, how many receiver channels you might need, that kind of stuff. So yeah, definitely, SDK can model all those.
This one might be maybe for Tal. I don't know. Someone's asking how they get trained on this.
Yeah, that's a great question. I'd say that you can go to help.agi.com/STK. That's help.agi.com/STK. We have a wide variety of tutorials on there, ranging from just getting started with SDK to covering more advanced ones, such as modeling GPS coverage and modeling GPS jamming. If you do not already have access to SDK, you can request an evaluation license by going to our main website, that's agi.com, and going to try us out. It's right at the top. Also on our site, that's agi.com, you can find information on getting SDK certified. So if you are interested, certainly check it out.
We have a couple other questions that are coming in now, fast and furious. What is the difference between SDK and SDK components?
I'll take that. So SDK is a desktop solution that provides navigation accuracy built into the tool. And I'm sure Tal can talk a lot more about SDK than just that short description there. But SDK components is not a desktop solution. It is the algorithms that make up what SDK can do and allow you to program against those algorithms individually. So if you just need GPS support, for example, and you don't need to know how to fly satellites to the moon, you would only need one portion of the SDK component set that we have. But you do have to program against SDK components, whereas you don't necessarily have to program against SDK, though you can if you want to.
Thanks, Ted. We do have some fairly detailed questions, which I'm going to have Ted follow up personally with those questions. I think it would take us down a deeper hole than I think we want to go with the webinar, but we'll remain on the line for a couple more minutes and see if we can pick out some of these. Here's a question. Can we import SDK commercial receivers with their specifications?
So I'm assuming you're asking if we can import GPS receivers from different manufacturers into SDK. And import by clicking a button, I don't think you can do that inside SDK, but we do support engineering level parameters in all of the GPS receivers. And so whether an SDK or SDK components, you can model down to the engineering level GPS receivers from many different manufacturers. So it's not a one-button import type function, but you can certainly model them in our tools.
Okay, that is exactly what they were talking about on that one. Can SDK generate simulated GNSS observables, pseudo-range, and phase at any time and location on the Earth's surface and orbit?
So our SDK tool does not do that, but our ODTK tool does do that. So that's an orbit determination toolkit, and I guess we'll have to follow up with you about that. I don't know if there's another webinar on ODTK or how they can do that, but that would be coming from that tool and not SDK. I see a question about, is your phased array model mature enough to easily build anti-jam capabilities, SERPA, et cetera? And the answer to that is definitely yes. And please get a hold of us, and we'd be happy to help show you how that works. I see some other fairly technical questions in there, Craig, and I guess what I'd like to do is follow up on those after.
Yeah, I think that's the best option on those.
Okay. With that then.
Well, you might be able to quickly answer the one that came in. I don't know. Are GPS receivers on LEO satellites susceptible to antenna gain?
Well, every GPS receiver needs an antenna, and that antenna is going to have a gain. So, yes, everything I talked about today about GPS receivers, they can be on the ground, they can be on a dynamic platform in the air, or they could be in space. All those same issues apply. The only thing that would not apply is something I didn't talk about, and that is possibly ionospheric effects or tropospheric effects. Ionospheric effects, if your signals are going through the ionosphere, can be mitigated pretty well through 2-frequency usage. Tropospheric effects wouldn't affect you at all in space, but though if you are inside the Earth's atmosphere, those are modeled pretty well inside the GPS receivers. That's why I didn't talk about those. So yes, everything I talked about applies in space except for atmospheric pieces. All right, in summary, I talked about many problems that can occur in typical GNSS systems. Again, some are easy to identify, some are harder. We do have tools that exist to mitigate these problems, so we'd be happy to show you how to use those to help you solve the problems you have in those situations. We've got a lot of expertise built into these tools. You can use them if you're just in the design phase, or if you're in the operations phase, if you're just using ground-based receivers, or if you've got receivers in the air or on space-based receivers like we just talked about. I did talk about SDK today, SDK Pro, SDK Coverage, and SDK Communications covers the issues that I talked about today, and then SDK Components as well with the navigation library and the navigation communications library. All right, if you'd like to learn more, you can take the training by going to this link here, or talk to an engineer, maybe you'll get tall, or look for future webinars by going to agi.com/blogs. And that's all I have.
Thank you, Ted. If you have any questions further, you can always email us at info@agi.com, or you can even contact us at support@agi.com if you have any technical questions. Those that I have reached out to directly that have a highly technical question, I'm going to have Ted or Tal follow up with you. Otherwise, I hope you enjoyed the webinar, and stay tuned for future webinars. Thanks.